Welcome to ECE 376 Embedded Systems, lecture number 12, Neopixels and Inline Assembler. Now this lecture I'm going to look at two things. One, we've already looked at the Neopixels in assembly. Now we're going to start using C code. With C, you can do a whole lot more than you can in assembly. So we're going to start out with just having it show up as a rainbow. Then we'll come up with a couple of flashlights where I can vary the brightness or vary the color. And finally, have it build a clock. So you're going to have like the red light spinning around as seconds, the green light being minutes, and the blue light being hours. Stuff that's really, really hard to do in assembly, but I can do that in C. Excuse me. In addition, there's inline assembly. The timing is critical on the Neopixels, so I really have to do that in assembly. So I need to mix programs. I'll have a C program with a high level doing stuff, and assembly program at the low level drive the Neopixel. How do you mix C and assembly together in the same program? That's what we're covering today. Now to start out, we previously looked at driving the Neopixel using assembler. Assembler has a lot of advantages. It lets you control the I/O pins directly. It allows for precise timing. But, and this is a big but, it is really hard to write, debug, maintain, and reuse assembly code. So generally, you frown upon using assembler. Do anything you can to avoid it. Sometimes you just can't avoid it. So what we're going to do is use the previous code in assembly as the low-level routines to drive it. And as a refresher, to drive the Neopixel, you've got to send it 24 bits of data. It goes green, most significant bit first, then red, then blue. When you do that, timing is critical. To send a bit, each bit has to be 1.2 microseconds long. That's 12 clocks. Logic 0 is a pulse that's 0.3 microseconds long, 3 clocks. Logic 1 is 0.7 microseconds long, 7 clocks. And a pause of more than 50 microseconds signifies a new message. So that's a real problem with C. In C coding, one line of C can take hundreds of lines of assembly. So I might not be able to send the message in time. If the C code takes longer than 50 microseconds, the Neopixel is going to interpret that as the end of message. So I really have to use combination C and assembly. This timing is really hard to do in C, but easy to do in assembly. So let's mix them. Let's have assembly and C in the same program. The C compiler allows you to include inline assembly. Pretty much all C compilers do that. What the C compiler does, it takes your C code, converts it to assembly, then assembly into machine code. If your code's already in assembly, that's really easy on the compiler. In high-tech C, the way you do that is use the command ASM. This will insert a single assembly command into your code. I can do multiple lines of assembly by using a #ASM, your assembly code, followed by # and ASM. Second problem you have is how do you pass data between assembly and C? I've got two programs running on my processor. They need to talk to each other. The C code will tell you how bright each pixel has to be. Then the assembly actually sends the bits, the ones and zeros, to do that. In Introduction to C, you're told never, never, never use global variables. The reason is it makes debugging hard, makes your code really hard to follow, and it's easy to mess up. If two different routines are using the same variable, it's hard to figure out what that variable should be. In this class, we're going to modify that. It's given a choice, don't use global variables. Sometimes there's not a choice. I want to pass data between C and assembly. Everybody can see a global variable. So likewise, the assembly routine can see it, the C routine can see it. That's one way to pass data using global variables. So we're actually going to break the rule that you did back in 173, enter it to C, and start using global variables. The compiler directives to do that. In assembly, if I say pixel equals 0, that just says pixel is a variable located at address 0. In C, I can say there's a variable pixel, it's 8 bits, it's located at address 0. Now C knows where the variable is, assembler knows where that variable is. And we're also going to use bottom-up programming. The low-level routines are assembler. The lowest level is just sending a single bit. I want to send a 0.3 microsecond pulse for 0, 0.7 microsecond pulse per 1. That's sending a bit. That's the assembly routine pixel 1. To send 8 bits, that's pixel 8. I'm going to call pixel 1 8 times. That'll send 8 bits. Then from then on, I'll start using C. I'll have a higher level routine where I pass red, green, blue, call pixel 8 that calls pixel 1. That way I can send a color. That's a single pixel. Call that a couple times, and I can send a message to the entire NeoPixel array. So what that looks like. Here's the subroutine called NeoPixel display. I'm going to pass 3 variables, red, green, blue. Slide that up a little bit. And what that does is I've got this global variable pixel. I'll write green to that global variable, then call my assembly routine pixel 8. It jumps down here to pixel 8, it calls pixel 1 8 times. Pixel 1 is the previous code. I'm going to set bit 0 of port D. This code right here is the address of port D. The way I figured that out is I actually wrote the C code, port D or RD0 equals 1, looked at the list file to see how it compiled, and this is how the C compiler interprets port D pin 0, RD0. So this is the previous code, and this is port D pin 0. This is address 0. Address 0 is pixel. That's a global variable at address 0. I'll then send the red light, then the blue light, and then return. So that's this subroutine. That's the interface between C and assembler. Using that, I can do a couple different programs. For example, NeoPixel 0 says in the main loop, let's turn on the red light, then 3/4 red, 1/4 green, half and half, and so on. What that looks like is this. This is the first pixel, that's all red. 3/4 red, 1/4 green is orange, half and half is yellow, then yellow-green, pure green. Then I'm getting the cyans, pure blue, and blue plus red makes purple. And this is kind of washed out. The camera doesn't like the neat lights shining right at it. And also kind of a reminder, if you take the code that's on Bison Academy and it doesn't run, probably what's happening is your code isn't offset. So go under Project, Build Options, Project. Under Linker, it needs to be offset by 800. If it's not offset, the code won't run because you're trying to overwrite the bootloader. You only get a partial program. Partial programs don't run. And the other thing to note, this program compiles into 2,966 bytes. That is 1,483 lines of assembly. A lot more assembly than I really want to write. So that's the first program. Second program. This is something which is really hard to do in assembly. Not too bad in C. Let's write a program so I can sit there and vary each color. I'm going to have RB5 and RB4, and these two buttons, controlling the red light, getting brighter and dimmer. The next two buttons control the green light, brighter, dimmer. And the last two control the blue lights, brighter and dimmer. Now what that looks like is the following. Here I've got the red light is 10, green is 0, blue is 20, so it's mostly blue. If I make the blue light dimmer, it's getting more and more red. Oops, there I went over wrap around. 0 minus 1 is 255. That just 2's complement. Camera didn't like that. If I add some green, red plus green makes kind of a yellow. And if I take out the red, oops, wrong one. There we go. Take out the red, I've got all green. Now start adding blue. Blue plus green makes cyan, or teal. And notice that only 8 of the lights are lit up. These last 4 are whatever they were last time I ran the NeoPixel. That was from NeoPixel 0, the rainbow pattern. If I only call it 8 times, the last 4 lights never see a bit pattern coming through. And so they just remember the old value. So that's the second code. I can sit there and vary the light levels. Again, it's kind of nice having the LCD display also, so I can see what this color corresponds to. This is 0, 8, and 12, where 255 is full brightness. And what the code looks like, I just have the previous code and have a couple if statements. One thing about this course, you can do almost anything with an if statement. It may not be stylish, but it works. I'm just checking the push buttons. If I have this one down, it gets brighter, otherwise dimmer. I'm not checking to see if you wrap around. So again, if I go past 0, so this is green, -1, 0 minus 1 is 254. That's really bright. That's wrap around. I've gone past 0, and I get the 2's complement. And then I display it. Another thing to note is in C, since timing is critical, I can't intersperse this. Once I start driving the display routine, don't do anything else. Just drive the NeoPixels. If there's more than a 50 microsecond pause between these two commands, it interprets that as the end of message. Last one is let's build a stopwatch, or a clock. I want to have the red light spin around as seconds, green light be minutes, blue lights being hours, and I'm going to speed it up so we don't have to sit there for 3 or 4 hours. One way to do that is I'll have an array for red, green, and blue. These are global variables. Everybody can see them, including the assembly routine. I'll have a subroutine. I'm going to pass it 3 variables. What is the time in seconds, minutes, and hours? And then clear out all the lights, and then turn on the one that is supposed to be turned on for the seconds, minutes, hours. Then the display routine, since timing is critical, when I call this, don't do anything else. Drive the first light, drive the second light, drive the third light. You think you could put this in an array. When I tried that, the for loop took too long and it started flickering, meaning it took more than 50 microseconds to finish off the for loop. If you're really stuck on timing, instead of having a for loop, I can just hard code it. I'll display the first light, the second light, the third light. Not pretty, but it works. And then the main loop just increments time. The seconds keeps on incrementing. Since I have 12 lights on my NeoPixel, when I get to 12, which is 0, I'll increment minutes. When minutes gets to 12, which is 0, I'll increment the hours. So when I download this code, compile it, and download, note that this is now 3,300 bytes, 1,673 lines of assembly. Way more lines of assembly than I ever want to write by hand. The C program isn't actually that bad. Trying to figure out how it works, I initialize the ports to output, clear port A, B, C, D, E, send a hello message on the screen, and then just count, display it on the LCD display, and then drive my NeoPixel. Again, when I start updating the NeoPixel, don't do anything else. Just drive the NeoPixel. The net result looks like this. I've got the red light spinning around, that's my seconds. Actually, 12th of a second. The green light is seconds, and the blue light is supposed to be minutes. Every time green wraps around, blue moves by 1. There it goes. So it looks like right around here is 0. That's some of the things you can do with a NeoPixel. Again, with C really opens up what you can do, but you have to have it inline assembly. Just because that low-level routine is timing critical, you almost have to have the low-level routine being assembly. That's sometimes done in industry. The low-level will be assembly, when I really have to have timing critical and speed. Anything else I want to write in C, so the code is reusable. And again, the other thing to note is that when I'm done, I got a lot of lines of assembly. What we completed was 1,700 lines of assembly for this code. Just a few lines of C. That's lecture number 12, NeoPixels in C for ECE 376.